So here, I was just going through the code and trying to understand it again. Yeah, so here, we also don't know the concrete lifetimes of the references that will be passed in. So we can't look at the scopes as we did in this thing 10-17 and 10-18. Okay, so let's go back 10-17 and 18. So we couldn't determine what the scope is. Okay, the borrow checker can determine this either because it doesn't know how the lifetimes of X and Y relate to the lifetime of the return value. To fix this error, we'll add generic lifetime parameters that define the relationship between the references so the borrow checker can perform its analysis. Okay, lifetime annotation syntax. Lifetime annotations don't change how long any of the references live. Rather, they describe the relationships of the lifetimes of multiple references to each other without affecting the lifetimes, just as functions can accept any type when the signature specifies a generic type parameter. Functions can accept references with any lifetime by specifying a generic lifetime parameter. Lifetime annotations have a slightly unusual syntax. The names of lifetime parameters must start with apostrophe and are usually all lowercase and very short, like generic types. Most people use the name apostrophe A for the first lifetime annotation. We place lifetime parameter annotations after the ampersand. Okay, so here we need to take note that we are placing lifetime parameter annotations after ampersand. So ampersand apostrophe A of a reference, using a space to separate the annotation from the reference type. Okay, so here are the examples. I think we covered this yesterday. This is plain reference, then this is a reference with an explicit lifetime, and this one is a mutable explicit lifetime. Mutable reference with explicit lifetime, so I think there's a space in between. Yeah, there's a space. One lifetime annotation by itself doesn't have much meaning because annotations are meant to tell Rust how generic lifetime parameters of multiple references relate to each other. Let's examine how lifetime annotations relate to each other in the context of the longest function. Okay, so if you guys are wondering why I'm reading this again, so it's like a review, because for sure, even for myself, I've already forgotten what I was trying to learn yesterday. So I do admit that this is a difficult topic. Yeah. To use lifetime annotations in function signatures, we need to declare the generic lifetime parameters inside angle brackets. Okay, so if you need to use it in function signatures, you need to place them inside angle brackets between the function name and the parameter list. So this is the function name, so it's here, and then the function parameters. Just as we did with generic type parameters. We want the signature to express the following constraint. The returned reference will be valid as long as both the parameters are valid. Okay, so as long as both the parameters are valid, the returned reference will be valid. This is the relationship between lifetimes of the parameters and the return value. We'll name the lifetime apostrophe A and then add it to each reference as shown in listing 10-21. So in the compilation, it was suggesting to do it like this also. So, okay, so how do we implement lifetimes in a function, lifetime annotation in a function signature? We place it in between the name of the function and then enclose in angled brackets, and then the parameters will have the annotation as well. And then this one will return apostrophe A also. Okay, so everything here is in apostrophe A. So the return value will be valid as long as both the parameters are valid. So it's like a guarantee that this one will be valid. The longest function definition specifying that all the references in the signature must have the same lifetime. Okay, so this should compile and produce the result we want when we use it in the main function in 10-19. Let's see, let's open up this one yesterday. So yeah, I copied that one. String, long string, result, xyz, calling the function longest. So as you can see, there's no compilation error. You run the code, and then you get this value. The longest string is long string, yeah, because the length of string 1 is greater than the length of string 2, which is y. So it will return string 1. Okay, the result is long string is long. Long string is long. Okay, let's continue. I think this is the explanation. Function signature now tells us that for some lifetime A, apostrophe A, function takes two parameters, both of which are string slices that live at least as long as a lifetime. Okay, one thing I've noticed yesterday, we come back to the code. This is str type. Yeah, because of this. So the str actually returns str, a string slice. Yeah, so it's not string. That's why we have the str here. But I think we can modify this a little bit by commenting this out, and then let string 1 equals long string long. So we'll get, okay, this one we need to change. So they are both string slice. It should work. Okay. Okay, in Okay, and let's read this one. I think this is one of the important points. We've just didn't have enough time yesterday to really understand what this is. So now's our chance. The function signature now tells Rust that for some lifetime A, apostrophe A, the function takes two parameters above, which are string slices that live at least as long as lifetime A. Function signature also tells Rust that the string slice returned from the function will live, okay, this one, as long as lifetime apostrophe A. In practice, this means that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the values referred to by function arguments. These relationships are what we want Rust to use when analyzing this code. Remember, when we specify the lifetime parameters in this function signature, we're not changing the lifetimes of any values passed in or returned. Rather, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Okay. Specify the lifetime parameters in this function signature. Not changing. We are not changing the lifetimes of any values passed in or returned. Rather, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Note that the longest function doesn't need to know exactly how long x and y will live. Only that some scope can be substituted for apostrophe A that will satisfy the signature. When annotating lifetimes in functions, the annotations go in the function signature, not in the function body. Okay, annotations go in the function signature. Okay, this is another important information here. The lifetime annotations become part of the contract of the function, much like the types in the signature. Having function signatures contain the lifetime contract means the analysis the Rust compiler does can be simpler. If there's a problem with the way the function is annotated or the way it's called, the compiler errors can point to the part of our code and the constraints more precisely. If instead the Rust compiler made more inferences about what we intended the relationships of the lifetime to be, compiler might only be able to point to use of our code many steps away from the cause of the problem. When we pass concrete references to longest, the concrete lifetime that is substituted for apostrophe A is the part of the scope X that overlaps with the scope of Y. In other words, the generic lifetime apostrophe A will get a concrete lifetime that is equal to the smaller of the lifetimes of X and Y. Okay, so X and Y only live inside the scope of the function. But when we pass here, in other words, the generic lifetime apostrophe A will get complete lifetime that is equal to the smaller of the lifetimes X and Y. Because we've annotated the return reference with the same lifetime parameter, apostrophe A, the returned reference will also be valid for the length of the smaller of the lifetimes X and Y. Let's look how the lifetime annotations restrict the longest function by passing in references that have different concrete lifetimes. Okay, so here I think it will complain because now string 1 is outside the scope of this function. String 1 as str, string 2 as str. Let's copy this. Okay, so it did not complain. It still works. Why? Is it supposed to work? In this example, string 1 is valid until the end of the outer scope. String 1 is valid until the end of the outer scope. Okay. String 2 is valid until the end of the inner scope. Yeah, because string 2 is here. End of the inner scope. So after this line. And result references something that is valid until the end of the inner scope. So result is valid until the end of the inner scope. Run this code and you see that the borrow checker approves. It will compile and print the longest string is long, string is long. Yeah. So it will approve. That's why you can see here there's no compilation error. It works. Next, let's try an example that shows that the lifetime of the reference in result must be the smaller lifetime of the two arguments. Lifetime of the result. Okay, result is here. Must be the smaller lifetime of the two arguments. Okay. We'll move the declaration. Okay, because the result is used, it is used here. Sorry for that. Let's continue. So here, where were we? Result variable outside the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. Okay. SSTR, string 2 is here. So the scope of string 2 is actually here. String 1, string 2, then result. Okay. But leave the assignment of the value to the result variable inside the scope with string 2. Okay, string 2 result. Then we'll move the print line that uses result outside the inner scope after the inner scope has ended. So this is the inner scope. So the print line, we're moving it out. How was it? Okay, here it's inside the scope. Okay. Attempting to use result after string 2 has gone out of scope. When we try to compile this code, we get this error. Because here result is being used. String 2 does not live long enough. The error shows that for result to be valid for a print line statement, string 2 would need to be valid until the end of the outer scope. So string 2 should be valid until the end of the outer scope. Because string 1 has not gone out of scope yet, a reference to string 1 will still be valid for the print line statement. However, the compiler can see that the reference is valid in this case. We've told Rust that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the references passed in. Therefore, the borrow checker disallows the code in 10-23 as possibly having an invalid reference. Try designing experiments. Okay. So I think this one we need to play around a bit. So it was done like this. Here we comment this out and then insert let result here. Then this, so this one will have an error. Okay, how can we fix this? If we, so one way to fix it is the print line should be here. Let's see. Yeah, correct. Print line should be here because the result is within the scope. If we remove this one, so it should still work. Yeah, because this function is within this scope. Let's put this back. So this one will complain. How can we fix this? So what we can do, one we can put it here. String 2. Oh, sorry, there. Just comment it out. Yeah. So result should be fine because string 2 is in this scope. Yeah. If we do something like oops. Yes. So this one will complain. Will it complain? No. This one is still possible. Yeah. Okay, so if I comment this, if I comment it here, and then this one will create an inner scope. Inner scope. Still works because string 1 and string 2 is here. So as long as X and Y are valid, yeah, anyway, these are inner scopes here. But if we move, which one shall we move? So this curly brackets doesn't mean anything actually. This is still fine. Yeah, because string 1, string 2 is still here. And we are using result here. But what is? It should still be fine, right? Nope. Why is that fine? The binding result is available in different scope in the same function. Yeah, okay, because result is here. If we remove it, then do it like this, should be fine. Yeah. So let's put this like this, and this one here should be fine. Nope. You comment this out. It means the print result should be here. Okay. So that's interesting. Okay. So we're done with experimenting. Let's move on. Thinking in terms of lifetimes. The way in which you need to specify lifetime parameters depends on what your function is doing. For example, if we change the implementation to the longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter. Following code will compile. You specified a lifetime parameter apostrophe a for the parameter x here, and the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. When returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. If the reference returned does not refer to the one of the parameters, it must refer to a value created within this function. Okay, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. Okay, and this one should match the lifetime parameter. Okay, so this one will not compile because now x doesn't have the apostrophe a because of this one. If the reference return does not refer to one of the parameters, if it does not refer to one of the parameters, it must refer to a value created within this function. It must refer to a value created within this function. Okay. So result as str. However, this would be a tangling reference because the value will go out of scope at the end of the function. Yeah, because you define it here outside the function, this will go out of scope. the value of result. Okay, you're pointing to the value of result, in which outside this function, it will, okay, this one will point to nothing. However, this would be a dangling reference because the value will go out of scope at the end of the function. Consider the attempted implementation of the longest function that won't compile. Yeah, so this will compile. The problem is that result goes out of scope and gets cleaned up at the end of longest. This one. After the scope of this function, it gets cleaned up. But we're saying that the return is a reference to the value here, which is already gone. Okay. There's no way we can specify lifetime parameters that would change the dangling reference. Yeah, that's true. And Rust won't let us create a dangling reference. In this case, the best fix would be to return an owned data type rather than a reference, so the calling function is then responsible for cleaning up the value. So in that case, I think the next solution would be, it's not a reference, but an owned data type. So I think this one will be removed. Let's see. Oh, oh, it's not there. This is an opportunity for us to try it out. Okay, remove, and then here. Okay, let's copy this. Comment this out. Then let's copy this. And then here we remove the apostrophe A. And so that's the one. That one will, of course, it will complain. So to fix it, we remove this one. Let's see. Okay, so now it complains. String slices. Still need ampersand. Consider using the ampersand, no, the apostrophe A. Function's return type should contain, return type contains a var value, but the signature does not say. There's one from X or Y. If we remove this, it's out. So we comment this out. String slice. Okay, because this one returns with an ampersand. So if we follow that one, we still have an issue. Whether it's far from X or Y. Quick fix. Still not allowed. Result is borrowed here. So there's no way of fixing this. Cannot do it like this also. Why? And the signature does not say whether it's borrowed from X or Y. Okay. If we remove this, the parts should be do here. Consider introducing a lifetime parameter. Yeah, so that is that part. Like result, string, string, string to result. Should be the same. Why do we have an issue? I think I already removed the annotation. Long guess. Expected name lifetime parameter. Missing lifetime specifier. This function's return type contains a borrowed value. Yeah, borrowed value. The signature does not say whether it's borrowing from X or Y. Yeah, but the return has nothing to do with whether X or Y. You can just say return. So it doesn't work at all. Okay, so it shows that we cannot do something like this. So let's put it back. So that one we cannot fix, or I cannot fix. Okay, so let's move on. Yeah, I think we understood why. Ultimately, lifetime syntax is about connecting the lifetimes of various parameter and return values of functions. Once they're connected, Rust has enough information to allow memory-safe operations that disallow operations that would create dangling pointers or otherwise violate memory safety. It really ensured memory safety first and foremost. Lifetime annotations in struct definitions. So far the structs we've defined all hold owned values. Can define structs to hold references, but in that case we would need to add a lifetime annotation on every reference in the struct's definition. Okay, structs we've defined all hold owned types. Oh, okay, so structs can hold references. Just like this. So a reference to str. But in that case, or string slice. But in that case, we would need to add a lifetime annotation in every reference in the struct's definition. Like this. Import excerpt. Let's see here. Okay, first sentence, novel, split, according to dot, next, unwrap. Next, unwrap. So I think there's some error handling here, if I remember it correctly. Next, unwrap. So this is still under lifetimes. Maybe we can copy this and put it there in our code. We just comment out main. Okay, so here, next option, yeah, some or none. Returns none when iteration is finished. And it will call next again. What does unwrap do? Returns the contained some value. Okay. Okay, unwrap will handle some from an option. Panics if the self value equals none. Okay, so it will throw a panic. And last time I think we did something with the panic. Oh, in this case we did not change the behavior. Let's take a look at the previous exercise. What was it? Traits. No, not this one. BI traits, cargo, not Tomo. Oh, not this one also. Generics. Generics, cargo. No, it should be error handling. Error handling, yeah. The Tomo. Yeah, here. So only when we compile with a profile release, then panic will abort. So it will immediately stop. Whereas by default, it's going to be a debug, which will show you a stack trace. Like similar to stack trace. Or they call it back trace in Rust. Okay, so what we have here now, first sentence would be the dot, and we have let I equals important excerpt, where you have part is the first sentence. Okay, so in structs, if we hold a field which is a reference to something, in this case it's a string slice, we need to have the annotation lifetime like this. So if we run this field, did it run? Yeah, I think it did. It's just that field part is never used. Okay, yeah, but it did compile. What would be the difference if this is not a reference, but it's str? Okay, so now this one will complain. Values of type str cannot be known. Compile time. Can we put in something like what I was trying to do? Because it's a field. Uh, Second. Cannot do something like this. We can only put, no, it should be at str. Percent str. And this one complains. Consider introducing a named lifetime parameter. What did we do in the struct last time? In structures. Source main. What did we have here? This one is unfortunately string. String. Okay, so string slice would have to be string slice should be, there's no other option, so we need to follow this one. Okay, the correct way of doing it is we do it like that. Okay, let's continue reading. This struct has the single field part that holds a string slice, which is a reference. So with generic data types, we declare the name of the generic lifetime parameter inside angle brackets. So it's just like the function. Okay. This annotation means an instance of important excerpt can outlive the reference it holds in its part field. Important excerpt can outlive the reference it holds in part field. So does it mean that no, I is important excerpt. The main function here creates an instance of the important excerpt, struct that holds a reference to the first sentence of the string owned by the variable novel. The data in novel exists before, okay, yeah. It exists before important excerpt. Okay. So after this, Novel doesn't go out of scope until after the important excerpt goes out of scope. So the reference in the important excerpt instance is valid. Hmm. Okay. As long as the important excerpt doesn't go out of scope. Oh, okay. So does it mean that we enclose this in mm, yes, I here. Right. Right. So print line. Okay, I sharp question mark. What is it now? Hmm? Ah, colon. Okay. Colon sharp question mark. So we'll see a different error. Doesn't implement debug. Okay, debug. Okay. Copy this. Call me Ishmael. Uh, what are we trying to do? Okay, important excerpt, first sentence. Uh, the data in novel exists before the important excerpt instance is created. In addition, novel doesn't go out of scope until after the important excerpt goes out of scope. So the reference in the important excerpt instance is valid. The data in novel exists, okay. Novel doesn't go out of scope until the important excerpt goes out of scope. Okay. Novel, first sentence. So first sentence doesn't go out of scope as well, because it's used here. Okay, so I is here. We just moved it there at the top so that we can call print. here. If we put it here, of course I would work. Yeah, okay. But if we do let it here, yeah, so this one will not work. Different scope. So we can remove this, then it should work. Okay. Lifetime elision. What is lifetime elision? You have learned that every reference has a lifetime and that you need to specify lifetime parameters for functions or structs that uses references. Okay, time parameters. Yeah. Functions, that was the first example. Structs, that's the one we did now. Important excerpt. However, we had a function listing in 4-9. Okay, 4-9. Shown again in listing 10-25. Okay. That compiled without lifetime annotations. We compile without lifetime annotations. First word as bytes. Okay, bytes for in bytes I iterate, enumerate. Okay, so it returned tuple I and the reference to item. I think we had this before. The reason this function compiles without lifetime annotations is historical. In early versions pre 1.0 of Rust, this code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signature would have been written like this. Okay. So this one breaks the original rule. Pre 1.0 of Rust, this code wouldn't have compiled. Yeah. Otherwise, it should have been written like this. Yeah, but I think if you write it this way, it will still execute. So we can try that one. First word. Yeah. It will compile. Then if we change it to use the lifetime annotation, how do we convert it into lifetime annotation? First, we need to put it inside the function name and then the parameters. And then the parameter itself, we put the apostrophe A with a space. And here, similarly, apostrophe A with a space. So we're saying, originally, since Rust 1.0, this is how it should be. Then this one should compile. Yeah. So it compiles. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotations over and over in particular situations. These situations were predictable and followed a few deterministic patterns. The developers programmed these patterns into compiler's code, so the borrow checker could infer the lifetimes in these situations and wouldn't need explicit annotations. Does it mean that it becomes like pattern over and over in particular situations, and followed a few deterministic patterns. So the developers program these patterns into oh so now it was programmed into compiler's code. So the borrow checker could infer the lifetimes in these situations and wouldn't need explicit annotations. So that you don't need to do explicit annotations. Oh, that's why it worked previously. As str, first word. Okay. What was the code we were trying to fix earlier? This one. So long as str. Result as str. What's the difference? Because ampersand s is here. This one. So so this one will only work if, even though we put this in, but we need to put x. Right? Whether it is borrowed from x or y. Because of this. Yeah. No? Still doesn't work. Sound of x. Yeah, ampersand of s. X. Ampersand of x. The pattern is similar. It's a difference. So we remove this one because it was saying after Rust 1.0, after a while, we don't know exactly when is that version where they program in the compiler the behavior of the borrow checker. Okay, so at okay. So if it's only one, so that one should work. This one, yeah. Remove this, then I'll bring this back at as str. Result is borrowed here. At x. Will it make a difference? No, because result is borrowed here. As str returns a reference to at str. So a reference to result, no, yeah, to the string from really long string. but it will be out of scope. So anything we define here will be out of scope. Okay. So that will not work. Yeah, but this ampersand x will work. Yeah. So it follows this pattern also. So here, we do it explicitly, then you need to do this part. And because it's only returning x or y, like this, that one should work. But once we bring in this, now it's going to be confused whether it's x or y. You can only return one. I think that becomes a limitation also. So to correct that, we put back x. Okay, so that's good to know. Meaning, originally it should be coded like this. Then somewhere along the way, that pattern was described as deterministic pattern, that they built in something in the compiler to be able to just do it like this. Oh, there's a space. We need to remove the space. Okay. Here, that explains that part. A piece of Rust history. Okay. Lifetime. The patterns programmed into the Rust's analysis of references are called lifetime elision rules. It's a cool sounding name. These aren't rules for programmers to follow. They are a set of particular cases that the compiler will consider. And if your code fits these cases, you don't need to write the lifetimes explicitly. I think it's safer to write the lifetimes explicitly so that the behaviors are, no, not the behavior, but the reading the code, it's more consistent. The elision rules don't provide full inference. If there is still ambiguity about what lifetimes the reference have after Rust applies the rules, the compiler won't guess what the lifetime of the remaining references should be. Instead of guessing, the compiler will give you an error that you can resolve by adding the lifetime annotations. So that's what we have experienced earlier. Trying it out here. So we forced longest to follow this, but then you have x and y. So if you have two parameters, that wouldn't work. You need one. I think it's more consistent if we stick to how it should be. I mean, for me, I would stick to how it should be. So that when you read the code, then it's consistent. Okay. compiler uses three rules to figure out lifetimes of the references when there aren't explicit annotations. The first rule applies to input lifetimes, and the second and third rules apply to output lifetimes. Input lifetimes, second and third rules apply to output. Okay. If the compiler gets to the end of the three rules and there are still references for each can figure out lifetimes, the compiler will stop with an error. These rules apply to function definitions as well as implementation blocks. The first rule is that the compiler assigns a lifetime parameter to each parameter that's a reference. So longest, imagine longest, you have x and y. So longest, x and y. So I think it's better if we illustrate it properly. So I'm assuming it will look like this originally, x and y, not the lifetime. Oops, comment out for now. So what it will do, x and y, lifetime parameter to each parameter that's a reference. So there will be apostrophe ax, and then here apostrophe a for y. Okay. In other words, function with one parameter gets one lifetime parameter. Okay, so if it's only one parameter, then you get one lifetime parameter. Function with two parameters gets two separate lifetime parameters. Oh. So it will look like this. Okay. Okay, so that's interesting. So if we try this one, remove this, it will not work because of x and y here. But if we say this is b, this one you have a, how do we add? Well, a comma b, a, oops, comma b, b. But now how do we know that the return would be a or b? How do we know that the return will be either A or B? Can we have B? Something like this? No. I was just guessing. And can we put a comma here? Be enclosed in parentheses? Something like that? No. Expected. Can we do something like that? No. Can we remove the space? No. Okay, but how do we... Can we do something like... We follow this one. This, comma, E, that. Oh, it's even worse. Okay, so we cannot do it that way. Maybe we'll get the answer in the next one. X, okay, B, okay, what did we miss? Yeah, y is b. Okay. Second rule is that if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. If there's exactly one, so this is for that one here, first word. That lifetime is assigned to all output lifetime parameters. Yeah. The third rule is that if there are multiple, okay, this is what we wanted, multiple input lifetime parameters, but one of them is at self or at mat self, because this is a method. The lifetime of self is assigned to all output lifetime parameters. Third rule makes method much nicer to read and write because fewer symbols are necessary. Okay, so let's pretend we're the compiler. Signature starts without any lifetimes associated with your references. Yeah, so here we don't need to put lifetime. There's only one. So what it will do, there's apostrophe A here, apostrophe A. Okay. Applies the first rule, which specifies each parameter gets its own lifetime. Oops. Second rule, yeah, second rule apply, and then it will look like this. For longest, okay, longest, this is what we wanted to fix. So A, B, yes, A, B, but here it's only ampersand str. Yeah, you see the second rule doesn't apply because there is more than one input lifetime. The third rule doesn't apply either because longest is a function rather than a method. So none of the parameters are self. After working through all the three rules, we still haven't figured out what the return type's lifetime is. This is why we got an error trying to compile the code in this thing. 10-20 is 10-20. Thing 10-21. Where's 10-20? Ah, yes. Yes, we will still get an error. Okay. Still get an error. Okay. It gets its own lifetime. This time we have two parameters, so we have two lifetimes. Okay. After working through all three rules, we still haven't figured out. This is why we got an error. Yeah. The compiler worked through the lifetime elision rules, but still couldn't figure out all of the lifetimes of the references in a signature. Because the third rule only applies in method signatures. We'll look at lifetimes in that context next to see why the third rule means we don't have to annotate lifetimes in method signatures very often. Okay. So it's still this one is still a mystery. We just abide by the rules. If x and y interchangeably being returned, then we don't know. Can remove the ampersand. Ampersand, no, ampersand apostrophe A. Yeah, it will still have an error. Still unsolvable. Yeah, because now it doesn't know whether it's y or it's x. So the only way to fix that is we return x, reference x or reference of y with here it should be b. Yeah. Lifetime annotations in method definitions. When we implement methods on struct with lifetimes, we use the same syntax as that of generic type parameters as shown in listing 10-11. Okay, so just like the generics, PL, how does the generic look like again? MPL. Struct, okay, struct we know, enum we know, IMPL, yeah. So it takes on this form. Type. Yeah. So type, and in this case it's annotation. First, we use a method named level, whose only parameter is self, and whose return value is an I32, which is not referenced to anything. It just returns I32. Cool. The lifetime parameter declaration of IMPL and its use after the type name are required, but we're not required to annotate the lifetime of the reference to self. Okay, so we have the annotation here. Although we are implementing a function, we're not required to annotate the lifetime. Okay, so here is an example where the third lifetime elision rule applies. We have a function but you have two parameters. Okay, but the first parameter is being returned. So if we imagine, okay, I think it's better if we copy this. Okay. So if we explicitly put in the ampersand a here, and by right, self should be ampersand a, and this one should be ampersand a, and this one should be ampersand a. But it will only work if we are returning the first parameter. Oh, it's wrong here. Lifetime name A shadows a lifetime name that is already in scope. Oh, probably because of this. That's already in, oops. Now it complains. Implicit elided lifetime not allowed here. Is it because this one is implicit? So now it's not allowed. I want it to be consistent. Okay, okay. Let's follow the rules. Okay, A here, %A, this one. Read through again. There are 2 input lifetimes. So Rust applies the first lifetime elision rule and gives both at self and announcement their own lifetimes. At self and announce, okay. Then because one of the parameters is at self, the return type gets the lifetime of at self. And all lifetimes have been accounted for. Okay. So it's okay if the second parameter is not the one returned. Is that correct? I might be wrong. Let's go through the rules again. It's important to understand the rule. Okay, first rule is that the compiler assigns a lifetime parameter to each parameter. That's a reference. Okay, understood. To each. The second rule is that if there's exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. Okay, to all output lifetime parameters. Third rule is that if there's multiple input lifetime parameters, but one of them, okay, it falls here, self, or at mat self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. Okay, so it's the third rule because of self. Okay, static lifetime. One special lifetime we need to discuss is static, which denotes that the affected reference can live for the entire duration of the program. Yeah, because it's static. All string literals have a static lifetime, which we can annotate as follows. S ampersand, okay, so apostrophe static is a lifetime. For the entire duration of the program. The text of this string is stored directly in the program's binary, which is always available. Therefore, the lifetime of all string literal is static. The lifetime of all string literal is static. Okay, so static, that is in stack. We have stack and heap. You must see suggestions in error messages to use static lifetime, but before specifying static lifetime for a reference, think about whether the reference you have actually lives the entire lifetime of your program or not, and whether you want it to. Most of the time, an error message suggesting that apostrophe static lifetime results from attempting to create a dangling reference or a mismatch of the available lifetimes. In such cases, the solution is to fix those problems, not to specify static lifetime. Okay. When do we actually use the static lifetime? Maybe not only for a string slice. Maybe. Don't know if that's possible. Generic type parameters, trait bounds and lifetimes together. Okay. Oh, that's the last. Let's see. Let's briefly look at the syntax of specifying generic type parameters. Trait bounds and lifetimes in all in one function. Okay, let's do some. Okay, let's not read the description there, but let's do the analysis ourselves. Module display longest with announcement. So you have okay, this is a lifetime A, but this is a generic. Okay, so X is lifetime A, string slice, Y is lifetime A, string slice, and N is a generic. It will take on this type. It returns lifetime A, where T is display generic type. Okay, so by doing this, T is actually display. Print line announcement X len greater than Y len X else Y. Oh, but this one returns A. Both are A. X won't be, it will be unknown. Okay, the compiler wouldn't know whether it's X or Y. It says here it will compile. This extra parameter will be printed using, okay, which is why display trait bound is necessary, because lifetimes are type of generic. And the declarations, okay, lifetimes are type of generic. The declarations of lifetime parameter A, apostrophe A, and the generic type parameter T go in the same list. Will it compile? Just curious. Because you have X and Y here. Let's see. Huh. Well, that is surprise. And we understand, and but this one here, percent %A, why will it work? Okay, this one I will remove. A, this should be A. This is A. And we have this. What? I thought we did this previously. What did I miss? Maybe later, once the video is finalized. I don't know how to call that. Once I can view my own live stream. Would have to check what exactly have I done. AAASTR worked. That's weird. Okay, that one will work. You put X here. That one will work. This one here. Yeah, this one will not work. Whether it is borrowed from X or Y. So the only way to fix that is to do something. That one was working all along. I don't know where I missed that. A, but this is only having one parameter. Okay, so I'll keep this here. That means this is the solution. It's good. We found our solution after all. Summary. Yeah. Generic type parameters that you apply code to different types. Traits and trait bounds ensure that even though the types are generic, they'll have a behavior the code you need. Traits is quite interesting. You learn how to use lifetime annotations to ensure that this flexible code won't have any dangling reference. It's to ensure safety. Safety against dangling references. All of this analysis happens at compile time, which doesn't affect runtime performance. Yeah. Because we are doing it at compile time. Believe it or not, there's much more to learn on the topics we discuss in this chapter. Chapter 18 discusses trait objects, which are another way to use traits. There are also more complex scenarios involving lifetime annotations that you will only need in very advanced scenarios. Very advanced. Okay, so as of now, we don't want to go to advanced yet. There's so much to learn here also. For those you should read Rust reference, but next you learn how to write tests in Rust so you can make sure your code is working the way it should. Okay, so I think we stop here. We'll reserve that for another day, so solely dedicated for writing automated tests. And then hopefully by weekend we'll have some time to build a real program. So I won't look into this now. Let's end here for now. All right, thank you so much for accompanying me in this journey in just starting programming, learning the Rust programming language. I wanted to thank my supporters. And then I wish you a nice evening. Thank you so much. Bye for now.